The first of the two substitution reactions we're going to look at is known as the SN2 reaction. This designation comes from a system of designating reaction mechanisms, and the symbolism in the name SN2 stands for substitution nucleophilic bimolecular. Substitution for the overall reaction process, nucleophilic for the fact that this is driven by a nucleophile, and bimolecular refers to the kinetic behavior of the reaction. In its simplest form, a nucleophile, Lewis base, forms a bond to a carbon that bears some sort of leaving group. Halide ions form very stable ions and can act as leaving groups. And that displacement results in a new compound where we've effectively substituted cyanide for the iodide that's in there. So in a more generic sense, nucleophile reacts with a substrate that bears some sort of leaving group. It is replaced when we form a new compound. The leaving group, usually in the form of an anion, but it can sometimes be neutral molecules, is the byproduct. The overall rate of the reaction is dependent both on the concentration of the substrate that bears the leaving group and the concentration of the nucleophile. And that implies that these two interact in the rate determining step of the reaction. You can imagine this process happening in three different ways in terms of the stereochemistry of the process. If you had a chiral substrate, the 1, 2, and 3 here represent different groups attached to the carbon, and so this is a chiral center. You can imagine the reaction occurring in such a way that the nucleophile simply replaces the leaving group, and you end up with essentially the same configuration that you started with. This is known as retention of configuration. You can imagine a scenario where the nucleophile does the substitution and you get an inversion of configuration. In the third scenario is that you end up racemizing. So substitution occurs, some of the product retains configuration, some of the product is inverted, and if you end up with a 50-50 mixture, that would be a racemate. In fact, what we find is shown here highlighted that the SN2 reaction typically leads predominantly, if not completely, to inversion of configuration. And this is sometimes referred to as the Walden inversion after the German chemist who had identified it in the mid-20th century. So why is inversion of stereochemistry observed? Why is this the preferred pathway? And it has to do with the orbital interactions during the reaction. So in this reaction, like we've talked about previously, we have a nucleophile with a filled highest occupied molecular orbital interacting with the lowest unoccupied molecular orbital of the substrate. And in these substrates, that lowest unoccupied molecular orbital is the anti-bond of the sigma bond between the carbon and the leaving group. And that's illustrated here. So this pair of orbitals you see here corresponds to the antibond with its node here between the carbon and the leaving group. When the nucleophile interacts with that substrate, it does so by a pair of electrons in some orbital on the nucleophile, and it turns out that the greatest overlap can occur with this lobe of the antibond, and that lobe is on the opposite side of the carbon from where the leaving group is. It's what's referred to as the backside of the carbon and leaving group bond, and we sometimes refer to this as backside attack. The front side substitution requires overlap with part of the antibond that's between the carbon and the leaving group, and it ends up being kind of sterically inaccessible. And so this is where the preference for the so-called backside attack comes from. So this inversion of stereochemistry can help us propose a mechanism for how the SN2 reaction occurs. And that proposal that is borne out by experiment is that this is a concerted reaction, meaning the bond making and bond breaking happen at the same time, that features a backside attack of the nucleophile and formation of a bond with the incoming nucleophile and breaking of the bond with the leaving group. You can imagine a curious scenario where you have iodide replacing an iodine. Um, but nevertheless, this can occur. And so we can imagine this occurring by the iodide ion donating a pair of electrons into that sigma star and breaking the carbon iodide bond. The transition state for that reaction is what's depicted here in brackets, where at the apex of the potential energy curve, we have a partial bond between the incoming iodide and the carbon. We have a partial bond between the carbon and the outgoing iodide. And the carbon essentially at that point is sp2 hybridized. So these additional bonds are arranged in a trigonal planar fashion. And the structure is essentially kind of turning inside out, kind of like an umbrella turning inside out in the wind. So putting that onto a potential energy diagram, we would see something like this, where we have our nucleophile and substrate. We would have to climb an energy hill to form this high energy transition state. In the transition state, we have partial bonds between the nucleophile, the carbon, and the leaving group. And then as we proceed to the products, we form the new bond and the leaving group leaves. Now, this sort of reaction where we have a species like iodine replacing iodine would be kind of energetically neutral, but more typically, what we would have is a reaction that is favored in one particular direction. And the only difference there is the reaction would be thermodynamically favored, and for some reason the product combination is more stable than the starting materials. And under those conditions, we would readily get reaction. But nevertheless, the reaction would be more or less the same. There are some subtle differences in the transition state. So as the nucleophile starts to come in, we start to form that bond between the nucleophile's orbital and the backside of the carbon leaving group antibond. Typically, we would find in these sorts of exothermic reactions that the transition state lies a little earlier along the reaction progress. And so you'll notice the nucleophiles coming in were not quite trigonal planar at this point because it's a slightly earlier transition state. But then as things proceed, we end up gaining energy or going to a lower potential energy. And so we have an overall favorable reaction. So there are consequences to the need for the nucleophile to interact with the sigma star orbital in that particular way, such that if you have a substrate that somehow prevents the nucleophile from accessing that orbital, it can hinder the reaction and slow it down, sometimes to a great extent. And here are kind of two illustrations of that. Over here, you can see that we have a T-butyl group with a leaving group on it. And what we find is that when leaving groups are attached to these sorts of carbons, where we have three alkyl groups attached to that carbon, that typically these SN2 reactions don't proceed. That there's too much steric hindrance, here illustrated by these methyl groups, and it is enough to prevent the nucleophile from getting close enough to starting to form a bond. And so we find these kind of substrates to be inert to this kind of substitution. Other substrates aren't necessarily inert, but they can be quite slow to undergo reaction because the nucleophile has to kind of find its way to that orbital, that sigma star orbital. And this is an example of that, where now the T-butyl group is here, but the carbon where the reaction is occurring here, there is enough room for the nucleophile to kind of nose its way in there, but the T-butyl group presents enough hindrance that we get a slow substitution reaction, but it nevertheless does occur. You can imagine other substrates where you'd find a similar sort of effect. Here we can see an example of a substitution happening where our leaving group is attached to a cyclohexane ring. In its most stable conformation, this bromocyclohexane would have the bromine in an equatorial position, and that would mean an incoming nucleophile, represented by iodide, would have to come in kind of across the top of the ring, and these hydrogens, these axial hydrogens impose some steric hindrance. And so again, the reaction will occur, but it's going to be much slower than it would occur on other substrates. The other consequence you can see is that we get inversion of configuration. So initially that iodine would end up axial, but of course once the product is completely formed, it can undergo chair-chair interconversion and form the more stable conformer. Some other aspects of the reaction we need to consider. One is the nature of the nucleophile. What type of nucleophiles are involved? It turns out some nucleophiles are more reactive inherently than other nucleophiles. Here, for example, we have nucleophiles that can react and more or less give the same product. In this case, we have a methoxide as our nucleophile displacing iodide. We form dimethyl ether. It turns out methyl iodide will also react with methanol, simply the conjugate acid of methoxide. It initially forms this protonated species, which is deprotonated to give dimethyl ether. Both of these are nucleophiles. They're both Lewis bases, have electron pairs they can donate, but it turns out the reaction overall is much more rapid with methoxide than it is with methanol. And it turns out that's a general observation. A base is always a stronger nucleophile than its conjugate acid. Methoxide is the base that is formed from methanol. And if you think about why this would be, it's primarily due to charge. The carbon leaving group bond is polarized. Carbon is somewhat positive, and leaving groups are somewhat negative. All of these substrates have that polarity. And so the attraction between that positively polarized carbon and the negatively charged methoxide is going to be far greater than the attraction between that positively polarized carbon and the only partially negatively charged oxygen of methanol versus the fully negatively charged oxygen of methoxide. So from a kinetic point of view, this reaction is going to be much more rapid than this one is, even though they both will occur. Now, it's important to stop here because I've been talking about something behaving as a nucleophile, and I've referred to acidity and basicity. And it's important to note that basicity and nucleophilicity are related, but they are different properties. Basicity is ultimately a thermodynamic property. It's based on an equilibrium constant. Nucleophilicity, on the other hand, is a kinetic property. It refers to the rate at which something reacts. So don't equate basicity and nucleophilicity. There is a correlation between the two, but they are in fact different properties. If you look at a bunch of species that are used as nucleophiles in these sorts of reactions, you can kind of rank order them in terms of their relative nucleophilicity. And again, this is talking about the rate at which they react with substrates. So what we see here is a bunch of nucleophiles commonly used in SN2 reactions. You can see that most of these are anions of some sort, but there are a few neutral molecules. Ammonia is in here, methanol is in here, water is in here. But these can all act as nucleophiles and do SN2 reactions on suitable substrates. But they don't all react at the same rate. So at the top, you can see we have grouped three excellent nucleophiles: cyanide, mercaptide or the thiolate ion, and iodine. At the bottom, we have what are referred to as fair nucleophiles, so things like acetate, fluoride, the methanol, and water, even chloride ions. And then these structures here in the middle are so-called good nucleophiles. And over here, you can see relative nucleophilicity. It basically refers to the relative rate. So if you have a given substrate reacting with, say, water, under a certain set of reaction conditions, and you change out the water with cyanide ion, it'll react over 100,000 times faster. So what can we glean from this? Well, there's a few things. If you compare species that have the same atom, that is reacting. So say hydroxide compared with acetate compared with water, then it follows that basicity pattern. Hydroxide is more basic than acetate. Acetate is more basic than water. We can also compare the halogens, for instance, iodide, bromide, chloride, fluoride. And in this case, it's not basicity. It turns out to be a different property. It turns out to be polarizability. Iodide is quite large. Its outer electrons are readily donated. As you move down, as you move up the halide group to fluoride, fluoride is a small, hard anion, holds onto its electrons quite tightly. So it's a somewhat poor nucleophile. Iodide, because of its large dispersed electron cloud, can donate its electrons. It's said to be a soft anion. It's a better nucleophile. We find that same relationship between sulfide and hydroxide. Sulfur is larger, more polarizable. It can more readily donate its electrons. It's a better nucleophile than the oxygen anion is. So there are some other trends within the list that we see here. So just to go through those in a little more detail, you can compare species that have the same atom, and if they are related species, such as hydroxide and water, then the negatively charged species will be more nucleophilic than the neutral species. And so you find that pattern with mercaptide and hydrogen sulfide, with amidion and ammonia. They have that same relationship. If you compare similar species that have a periodic relationship, so for instance, fluorine, oxygen, and nitrogen lie in the same period on the periodic table. If we compare their anions, then what we will find is that nucleophilicity decreases from left to right, and it follows increasing electronegativity. Fluorine holds on to its electrons very tightly, whereas nitrogen has a lower electronegativity. It can donate electrons more readily, which is what a nucleophile needs to do. You have to be careful when you make these comparisons that you're comparing analogous species. So for instance, we can compare oxygen to ammonia. The oxygen and nitrogen are in the same period. Nitrogen's less electronegative. It's a better nucleophile. Phosphorus and sulfur can be compared as long as they're similar species. Phosphorus has a lower electronegativity. It's a better nucleophile. Sulfur has a higher electronegativity. And then finally, I alluded to this on the previous slide, you can compare species that lie in the same group on the periodic table. And there we find that it's size and polarizability. Typically, larger species are more polarizable and are better nucleophiles. So within the halogen group or within the oxygen group on the periodic table, we find the same patterns. One complicating factor is that nucleophilicity can be highly solvent dependent, meaning nucleophilicity changes with the medium in which the reaction is carried out. And here's some data that kind of illustrates what happens with halogens if you change the solvent. So look closely here under the arrow in each one of these. We have a different solvent. So in this first example, the reaction is taking place in water as a solvent. In the second example, it's taking place in acetone as a solvent. And the last example is a gas phase data. And if we look at this, we can find there's some really curious things that happen. So for instance, if we look at iodine, and we go down here, we find the relative rate is that iodide is very reactive in water. It's much slower to react in acetone, and basically doesn't react in the gas phase. Fluorine is curious. It doesn't react in water, doesn't react in acetone, but is quite reactive in the gas phase. So we've got a kind of a reversal in reactivity. Bromine kind of behaves like iodine. It's reactive in water, less reactive in acetone, very unreactive in the gas phase. Chlorine follows that same pattern. The other side of the reaction is the substrate and its leaving group, because we're ultimately going to break the bond between carbon and the leaving group. So the nature of the leaving group has an effect on the rate of the reaction. Typically, what we find is the more stable the leaving group, the faster the reaction will be. So that means that by breaking the bond and forming a new species, if we form more stable species, that's going to be energetically more favored. So if we look at this, at the leaving groups that are formed, what we can do is kind of compare the leaving groups to their conjugate acids. And when we do that, we find that good leaving groups are conjugate bases of strong acids. And they're typically conjugate bases of strong acids are very weak bases, very stable anions. Weak acids, by contrast, have relatively strong conjugate bases, and that's an indication that those ions are much less stable. And that's kind of the overall pattern. So more stable the anion is, better it is as a leaving group. The less stable the anion is, the poorer it is as a leaving group. Now, so far we've been looking at substrates in the examples that you've seen where the leaving group was a halogen typically, and we'll look at other leaving groups. We've looked at alcohols recently, and so you might think that alcohols could react in an SN2 reaction such as this, where a nucleophile comes in and displaces it. It turns out this is problematic. And it's problematic for two reasons. One reason is that hydroxide is a really poor leaving group. It's an unstable, highly reactive anion. That's why it's such a strong base. The other is the medium in which you carry out the reaction. Normally, SN2 reaction media are somewhat basic because the nucleophiles are usually anions, and so they can be slightly basic salts. On the other hand, if you could carry out the reaction under conditions where you could protonate the hydroxyl group, you can convert the alcohol into its conjugate acid, where we have an oxonium ion attached, and that is essentially a water molecule. That's a much better leaving group. So if a nucleophile could encounter this, we would easily break that carbon-oxygen bond. Where if we don't protonate, we're not going to break that bond because of the unstable hydroxide ion that we form. So in the reactions of alcohols, one way to carry them out is to use hydrogen halides. And hydrogen halides provide kind of a two-part reactivity. One is they're strong acids and can protonate alcohols. That transforms them into their conjugate acids with these oxonium ions, which bear essentially a water molecule as a leaving group. The other is hydrogen halides. The other partner is a halide ion, which are good nucleophiles. So once protonation has happened, then the halide ion can do the SN2 reaction. And so this is a way of carrying out SN2 reactions on alcohols where it's essentially a two-step process. Protonation to form the oxonium ion, and then substitution in the SN2 sense. So it's worth drawing out that mechanism in a little more detail. So let's do that now. So here we have the reaction of 1-propanol in hydrochloric acid. Now, you'll notice the way this is written. It says HCl and water. And now what we need to do is step back and say, what do we know about HCl and water? And the answer is that as soon as you put HCl into water, you don't have any HCl anymore, because you know that hydrogen chloride is a very strong acid. And so you get proton transfer in a complete sense to form hydronium ion and chloride ion. So in the solution, there's no HCl. All there is this mixture. So even though chemists write this, we understand that it means this. All right, so now what happens in this reaction? that allows for the substitution. So the first thing that happens is we protonate the alcohol. And as we just said, the proton donor isn't HCl because it completely ionizes the solution. It must be H3O plus. So when we write our mechanism, H3O plus is our proton donor. So we get transfer of a proton to form this oxonium ion. And now we get reaction with the chloride ion. To do the SN2. And there's our mechanism for the SN2 reaction of an alcohol under acidic conditions. It turns out there's a similar reaction that occurs between strong acids and ethers, and that's shown here. So rather than an alcohol, we have an ether here. And this is something that happens primarily in the presence of hydrogen iodide or hydrogen bromide, or hydroiodic or hydrobromic acid. It doesn't happen to much extent in hydrochloric acid, and it doesn't happen at all in hydrofluoric acid, which are, by comparison, much weaker acids than HI or HBr. And the overall result is cleavage of an ether. Now, the reaction is somewhat slow, and you have to add heat in order to get it to go at an appreciable rate. And so you'll notice here that we have indicated reflux, meaning we're heating these reactions to the point where the water is refluxing. And the overall result is the cleavage of one of the carbon oxygen bonds. There's a preference for cleaving the bond to the less substituted carbon. So if you look at the products over here, and likewise here, this is the less substituted carbon, primary carbon on this side. We have a secondary carbon on the other side. We end up with the substitution occurring at the primary carbon. Up here, we have a primary carbon, we have a secondary carbon, substitution primarily occurs at the primary carbon. All right, so what's going on in this reaction and why are we talking about it now? And the answer is it's very similar to the mechanism we just drew. So again, we have this combination of HBr and water, and of course HBr in water would completely ionize to form hydronium ion and bromide ion. All right, so what's happening in this reaction? And what's happening is we're going to protonate that oxygen in the same way that we did with the alcohol. So the oxygen's behaving as a base. So we end up with this protonated species, and that species can now undergo SN2 reaction. And it can undergo an SN2 reaction much in the same way that the alcohol did, like so. So what's happened that allows this to happen is we've made a good leaving group much in the same way that we turned a hydroxyl group into a water molecule to make it a good leaving group. In this instance, we've turned part of the ether into a good leaving group in the form of ethanol, of an alcohol. So we've learned that alcohols are good electrophiles when the hydroxyl group is protonated and becomes a good leaving group. And so that was what we've just been illustrating, that if you protonate the oxygen, turn that into an oxonium ion, you have a good leaving group in the form of a water molecule, and you can readily get SN2 reaction. The disadvantage of using a protonated alcohol is that strongly acidic solution is required. This is a hydrobromic acid solution. And most nucleophiles are also basic. And that's a problem because if we want to introduce a different nucleophile other than a halogen, because these acids are all hydrogen halides, if we want to introduce a different nucleophile, so for instance, here's an alkynyl anion. We'll talk about how to make those later on. If you want to introduce that and try to get it to do an SN2 substitution, it turns out the SN2 substitution is a higher energy pathway, and there's an alternative. This species is also a good Bronsted base, and this substituted oxygen is very acidic. And so the low energy pathway for this to react is it actually just deprotonates the oxygen, and you've reformed your alcohol, and that's presumably not what you wanted to do. So that could be problematic, that there's a very limited case for how we can do substitutions with alcohols, with these hydrogen halides. How do I get other nucleophiles to do substitution on an alcohol of some sort? And there's a solution. So the solution is to modify the alcohol, to make a derivative out of it that turns the OH group into some side of group that can act as a good leaving group. And we have a variety of tools for that, but the most common one that organic chemists use are what are called sulfonates. So alcohols can be very easily converted into sulfonate derivatives. And that's shown generically here, where here we have just a basic structure for an alcohol. And we're going to react that with a sulfonyl chloride. It has this structure here. And it turns out these react quite readily, where the alcohol essentially does a displacement, and after deprotonation, we end up replacing the hydrogen with the rest of this group. So this is a sulfonate group. It's essentially a sulfur ester. The way that formation happens is kind of illustrated here, where the oxygen displaces the chlorine to produce this. This solvent that we use for the reaction is a basic compound known as pyridine. The pyridine deprotonates this, and we form this ester. And these are so common that they have some kind of common names. It turns out this particular example that's shown here uses this sulfonyl chloride that's known as para-toluene sulfonyl chloride. The little P here stands for para substitution, which means that the groups are attached on opposite sides of this ring. It's so commonly used it has an abbreviation, TSCl, and it's called tosyl chloride. Once the reaction occurs, it forms this ester, and these are stable compounds. You can make these and crystallize them and put them in a bottle on the shelf, for instance. But what we've done is we've derivatized our alcohol. We've turned our alcohol into a different structure, but we still have that RO bond over here. And the beauty of these is this is actually an excellent leaving group. So we can take that compound after we've made it. Here's the tosyl group abbreviated as that TS, and we can react it with all sorts of nucleophiles. So we started off this discussion using iodide as a nucleophile. It's often used as an example because it's such a good nucleophile, and it can do an SN2 reaction. And here you can see another example of that inversion of configuration. And the leaving group is this tosylate ion. So why is this tosylate ion such a good leaving group? And the answer is it's a resonance stabilized anion. It's very good. It's like a sulfate, but an organic derivative of a sulfate. And you can actually draw a series of resonance structures that shows that negative charge is delocalized around the oxygens on the sulfur. So it's a very simple tool. Take an alcohol, make a tosylate, and then you can do whatever SN2 reaction you want to. There are some other really good reactions for converting alcohols into substituted products. Another one of them is shown here. This is the SN2 reaction using a reagent called thionyl chloride. Now, thionyl chloride is kind of a volatile, noxious liquid. It isn't really for the faint of heart working in the laboratory, but it reacts quite readily with alcohols and converts them specifically into alkyl chlorides. Works quite well for alcohols that are primary or secondary alcohols. Tertiaries essentially don't react. And you get the corresponding chloride. And here's two pretty simple examples. You'll notice that pyridine, that molecule I mentioned before, is the solvent here that's often used. And the reason for that is one of the byproducts of the reaction is hydrochloric acid. And it's often problematic to have strong acids around with organic molecules. And so you use a solvent that reacts with that hydrochloric acid. The way this reaction works is the thionyl chloride initially reacts with the alcohol to form a derivative like the ones you see here, and that derivative can undergo an SN2 reaction. There's also a possibility for another pathway, which we'll talk about later on, where the derivative that's formed in the reaction actually fragments to form a carbocation and a halide ion. But for the time being, since we're talking about SN2 reactions, the notion is that this happens here, and this is mechanistically, you can see how this breaks down to give sulfur dioxide and chloride ion. Other reagents that can be used to convert alcohols into alkyl halides are phosphorus halides, and there are a number of these. Phosphorus trichloride, phosphorus tribromide, phosphorus pentachloride, and these are all compounds that react readily with primary and secondary alcohols and convert them into the corresponding chlorides and bromides. And again, this is a reaction that's occurring because there's ultimately a good leaving group produced. These all produce these phosphorus byproducts. They're pretty simple reactions to carry out in the laboratory. They're easy to purify. And here's two examples from the literature. The primary alcohol here, secondary alcohol there that undergo this transformation. So what's happening in these reactions that allow the reaction to occur? I can illustrate that with the reaction of this alcohol with phosphorus tribromide. So again, we have one propanol, and the reaction occurs, first by displacement of bromine from the phosphorus tribromide. This forms what's known as a phosphate ester. You'll notice that we broke a bond to bromine, so we've actually produced a bromide ion. And it's that bromide ion that does the SN2 reaction. And curious feature of this reaction is all three of the bromines are reactive. This species can actually go on and continue to react with additional alcohol. I'd mentioned that solvent effects are really important, and if you use the wrong solvent, it can have a very slow reaction. If you use the right solvent, it can be a very rapid reaction. So why is that? Well, it depends on the nature of the particular substitution. So there are SN2 reactions that involve neutral nucleophiles interacting with substrates, and there are also SN2 reactions that we have charged species. In each case, there's going to be a transition state, and in the transition state, there's going to be some distribution of charge. Typically, we find the charge is going from the nucleophile toward the leaving group. So from the nucleophile toward the leaving group. In the transition state, we're going to have partial charges. So whatever charge there was on the species that was the nucleophile, it's going to diminish. So if it was neutral, it's going to become somewhat positive. If it was an anion, it's going to become less anionic. As the leaving group leaves, it's going to take electrons with it. So if it was a neutral atom, it's going to start to become an anion. If it was a cation, that cationic charge is going to start to decrease, and then we're going to proceed to the products. Depending on the solvent you use, it can have a stabilizing or a destabilizing effect on the intermediate. Typically, we find that we want polar solvents because there are distribution of charges in these transition states. And so the solvents need to help stabilize those. Here's an example of how that would play out with solvents of different polarity for that first reaction. So we have neutral reactants. They would interact with the two solvents almost the same way, but the transition states would interact differently. If we had a more polar solvent, it could interact more strongly with these partial charges and we would have a lower energy. If we had a less polar solvent, it would interact less with the partial charges and we have a higher energy. So the result would be the reaction would be faster in the more polar solvent. You might also find that the reaction would be more favorable in the more polar solvent because in this case we're forming ionic products. It would be less favorable in the less polar solvent. So you have to think about how the solvent interacts with both the transition state, because it can alter the height of the activation energy and thus the rate of the reaction. And you also have to consider how the solvent will react with the products, because that can increase the delta G of the reaction or decrease the delta G of the reaction. Here's that other reaction where you can see that the less polar solvent and the more polar solvent are going to have effects in the other way, on the other end of the reaction. They're going to interact very differently with these charged starting materials. The more polar solvent would stabilize them and might make the reaction unfavorable. It might actually stabilize the reactants so much that you find the reaction isn't thermodynamically favorable. A less polar solvent can have the effect of destabilizing the starting materials, which actually is beneficial because it would make the overall reaction more energetic, overall energetically favorable. On the other hand, they're going to interact with the transition states in different ways, again, because of those partial charges. The more polar solvent would stabilize it to a greater extent than the less, but if there's a big change here in the starting material, you ultimately have a lower activation energy for the less polar solvent. So solvent choice can be critical. If you make the wrong solvent choice for a particular reaction pair, you can almost shut the reaction off. And finally, I want to mention the fact that a lot of what we do in the organic lab is things that we find in Mother Nature. So for instance, in the organic chemistry lab, we know that sulfur is an excellent nucleophile, and we'll do substitution reactions to form these sulfonium ion species. We also know that those sulfonium ion species are really good species for undergoing SN2 reactions themselves because they bear essentially a very good leaving group in the form of a sulfide. And so you can take a nucleophile, just shown here as some generic alkoxide ion, and it will react with this trimethyl sulfonium ion, and we get the SN2 reaction, and it happens quite readily because we get the dimethyl sulfide. Well, it turns out We find this very thing happens in Mother Nature. This is S-adenosylmethionine, SAM for short, and it's nature's methylating agent. So it's a bigger, more complex molecule, but you notice at the heart of it, the reactive part of it, has that same electronic structure where we have this sulfonium ion and a methyl group. And so it will react with nucleophiles in exactly the same way. This is nature's methylating agent, and it methylates because it activates the sulfur to reaction as a very good leaving group. It just turns out to be a much bigger leaving group than we find with our other compounds.